Today we are going to go back to chapter 10 to talk about parametric surfaces. This leads us directly into surface integrals, so it actually works really well placed here versus doing it back when we did chapter 10. So parametric surfaces are surfaces that we can describe using two parameters. We are already accustomed to using parameters to describe lines in space. We can parameterize them in terms of t. And we also have parameterized surfaces when we've used r and theta, and also when we've used rho, theta, and phi to describe surfaces. And the reason we can take a 3D surface and describe it in terms of two parameters is when you think of us, for example, walking on the surface of the Earth. When we walk on the surface of the Earth, such as this globe here, or this sphere, you can consider yourself going in one or two directions. So because we are actually walking on the surface and not considering the inside, there are two ways we can go on the surface. So we can use two parameters to describe that surface. So today we're going to talk about parameterizing surfaces, and we're going to talk about how to interpret surfaces that have been parameterized. So far, we have worked with different forms of surface equations. For example, if we look at a sphere, we have looked at it in terms of an implicit form, where all of the variables are on one side, such as x squared plus y squared plus z squared equals some constant c. So, for example, a sphere of radius 4, we could write it in implicit formula, where again, all of the variables are on one side, a constant term is on the other. We could write it explicitly in terms of one of our variables. Typically, we did this in terms of z, so we could orient things in terms of the xy plane. So if we did that in this case, z would be plus or minus the square root of 16 minus x squared minus y squared. But we could also think about how we would parameterize this in terms of two different parameters. Now, those two different parameters can be any two parameters. In the textbook and in general, they use the parameters u and v, but you can parameterize in terms of x, y, or z. You could parameterize in terms of r and theta. You could really use any two parameters, whatever makes sense. Because this is a sphere, I'm going to think of this in terms of spherical coordinates. So in terms of our spherical coordinates, we know that because it's a sphere, I'm going to define r to be, rho to be 4, because rho is defined as the distance from the origin to, our surface. So if I define rho to be 4, then x would be 4 sine phi cosine theta. And if you look back through our definitions of spherical coordinates, you can look these up, but it would just be rho sine phi cosine theta, but here we're plugging in 4 for rho because it's a sphere of radius 4. Y would be 4 sine phi sine theta. And then z would be 4 cosine phi. And again, these were given in chapter 9, which was a while ago, but here we're going to use them in terms of this specific surface just to show how we would write the equation 3 different ways. 2 of them are using Cartesian coordinates, and then these are given parametrically in terms of the parameters phi and theta. And so today we're going to kind of delve into parameterizing instead of just one variable, parameterizing in terms of 2. And so the way this can be written is you can write them in terms of the different parametric equations, or you could write it as just one big vector valued equation, r in terms of phi and theta, then be 4 sine phi cosine theta I plus 4 sine phi sine theta j plus 4 cosine phi k. And you'll find these two used interchangeably just depending on what your needs are. Any questions so far? So if we look at, for example, a cone, just our standard cone, implicitly, we could write that as z minus, or actually let's look at explicit first. Z would equal the square root of x squared plus y squared. This was the general equation of a cone that we learned when we learned about different surfaces. Like we learned about our paraboloids, our ellipsoids, our hyperbolic paraboloids, and that was the equation we learned for a cone. If we wanted to write this implicitly, we would just put all our variables on one side, and then our constant, which in this case 0, on the other side. Now to write it parametrically, we could go two ways. We could keep it with Cartesian, so that would look like this. Parameterizing in terms of x and y, we could keep xx, y would stay y, but then z is defined as the square root of x squared plus y squared. And while this is true, the integrals tend to be rough with the z being that, and the boundaries can be rough, which is why we introduced polar form, cylindrical form. So if we go to polar, that's yet another parameterization. So we could then parameterize in terms of r and theta, and then we get our cosine theta for our I, our sine theta for our j, and then what would our k be? Yeah, k would be r. Because if r squared is x squared plus y squared, then z would equal r, and we know z equals r is the parameterized equation of a cone. So this is cleaner in almost all ways in terms of integrating and differentiating. So all of our integrals and operations tend to be cleaner that way. And I think we've seen that again and again with our triple and double integrals. Questions on that? So let's talk about a flat surface. Let's say we wanted to write the parametric vector equation of a plane. This is the general form of it. It involves the position vector that the plane travels through. And so if we know a point that the plane travels through, we can just write that point as a position vector. And then we need to know two vectors that the plane includes. So in this case, A and B are direction vectors that are in the plane. Those are both because they are vectors. And U and V are our parameters. And it's the easiest way to write the vector equation. It doesn't involve any cross products. And it would be the parametric vector equation of a plane. So for example, if I'm asked to write parametric equations for a plane that goes through the point 1, 2, 3 and contains the vectors -2, 3, 1 and 4, 0, 2, it's really just a plug-it-in situation. So the parametric equations, if I want to write it in vector form, it's r of u comma v would equal the position vector, which is just 1, 2, 3, because any point can be written as a position vector, plus one of the direction vectors times u, plus the other direction vector times b. So that is the vector valued equation of the plane. If I wanted to write the parametric equation, so that's like split up into x, y, and z, that would be x equals 1 plus negative 2u plus 4b. So just splitting it up in terms of your x, y, and z components. Y would equal 2 plus 3u. Yep, and then z would equal 3 plus u plus 2b. So that's just breaking it down. And I just wanted to remind you then how, given we know this information about two vectors that are in the plane and a point the plane travels through, how we would write the Cartesian equation for the plane, to remind you how we did that in chapter 9. Do you all remember? Yeah, and the cross product of two vectors in the plane give you the what of the plane? The normal. Yep. So if you have the plane and you know the normal is ABC, and ABC are the coefficients of the Cartesian equation of the plane. So let's do it. So the cross product, we just got a bunch of experience doing it with the del yesterday. So we get 6 going for the I, positive 8 for the negative j, and the k is going to be negative 12. So it's 6x plus 8y minus 12z equals d. I always like to scale that before I solve for d, just so my numbers are a little easier to work with. And then we'll substitute in the point that we have. And I got negative 7 for d. Anyone else get that? So if asked, you have many different versions of plane equations. You have the Cartesian version, and you have the parametric equations, and then you have the vector value function with the two parameters. Questions on that? Abhi? Totally up to you. So what we are going to do now is watch a video that describes how, using parametric equations, you can picture what the 3D surface looks like. And they have some animations in the video that I think are really useful to help it come to life, which I really couldn't do justice here in 2D. So we're going to watch this, I believe, 6-minute video. And I think I'm going to show you the homework, and then you can write that down, and then we'll do the video.